and evaluate it. So, what's the idea again? When is correlation the tool of the devil? When somebody uses it to argue for causation, because correlation and causation have nothing whatsoever to do with each other. And I was happy to see people seem to be getting there. Here's an example of a correlation problem. Here are what the numbers are. The x's go between 1 and 9, and the y's go between 70 and 130. This might be a short intelligence test that somebody's trying to use to predict a larger intelligence test with a mean of 100, standard deviation of 15. Maybe you're going to be a school psychologist and be deciding whether or not to give a full intelligence test to a kid whose parents are saying, I wonder if this kid belongs in special ed or should be promoted and skipped a grade, or various other questions being made on behalf of a child by parents and teachers. And you want to give a preliminary test before deciding whether to give a more complicated one. Or maybe you're trying to predict how many crimes somebody's going to commit if they're let out of jail. Maybe you're trying to predict which couple is going to get divorced, if this couple is likely to get divorced, or if this person is going to commit crime against somebody else. Or is there going to be violence? Is this person going to be a violent person if you let him out of the mental hospital? So there's a correlation between what's on this. Can you tell what the correlation is? It's kind of hard to tell, isn't it? Right? Now, if you knew nothing, what would your best guess be if we're playing the variance game? Remember, that's where you make a guess and we take the difference between your guess and what it actually is and square it, and that's what you have to pay in dollars after class. Right? What do you think's on the other side of the 9?
3.
She guesses 3. It's 115. So 115 minus 3 is 112 squared. That's more than $10,000. All right, after class. That's why she was smiling. What do you think's on the other side of the 5? Now, if you knew nothing else, there's a relationship between the x's and the y's. Here's the y's. They have a mean of 100. What should you guess if you're playing the variance game? 100. And if you guessed 100, how much would it cost you on average? Well, the standard deviation is 15, so on average it will cost you 15 squared. That's $225 on average if you guessed 100. But you can do better than that. So here's where you don't know anything except the mean. But if you know x, you'll be able to cut down. Instead of costing you $225, it'll cost you less. All right? So if you know nothing else, guess 100, but not 3. Okay. What do you guess? What?
20.
20. Okay. It's 100. That's 80 squared dollars.
100.
She guessed 100. It was 100. You guessed 100 is 115. The difference is 15 squared, $225.
100.
Was 100. 130. 30 times 30, $900.
115.
Was 115. ESP he thinks he has. What's that?
100.
She guessed 100. It was 85, so it's $225. All right, so what should you do to do this? Let's see if there's a relationship between, it's not really apparent. And if you're a clinician, these are cases that come in, you're sort of learning this by experience. There was a 3 that went with 100, there was a 5 that went with 100. People can't remember all of this and calculate it. So one method for dealing with it is to draw a scatter plot. So here's how to draw a scatter plot. We're going to put the values of x on the x-axis. We're going to put the values of y on the y-axis. Oh, the lines aren't very good, but it helps if you've got graph paper. So 70, 85, 100, 130. So here's the values of y, here's the values of x. Let me fix this one a little bit. Now we're going to draw a scatter plot. And each case corresponds to 1 point. So the first case is 3, which goes 3 on the x-axis. I go up to 100 on the y-axis, and I put a point there. Then there's a 5 that goes with a 100. So I put a point there. Then there's 3 that goes with a 70. And a 5 that goes with a 100. I'm moving it a little to the side so we can count it up later. Another 5 with a 100. A 5 with a 115. Everybody clear on how I'm doing this? A 1 with an 85. A 5 with a 100. 5 with an 85. 3 with an 85. 9 with a 115. 7 with a 115. 7 with a 100. 7 with a 130. Should be 14 points there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there should be as many points as there are cases. This is called drawing a scatter plot. And Cowlett has some examples of scatter plots in which he's trying to teach you how to look at this picture and see the magnitude and the direction of the correlation. You'll see that larger x values go with larger y values, and smaller x values go with smaller y values, and that means you have a positive correlation. Sometimes people draw kind of an ellipse around the points, which is the shape of the distribution if it's a bivariate normal. I'll say more about that later. And so the fact that that has positive slope means it's a positive correlation. We're going to calculate the correlation. So correlation coefficient R sub xy is equal to the sum from I equals 1 to n, z sub x sub I, z sub y sub I, divided by n. So that means we need to convert each score to a z-score, multiply them, add them up, and divide by n. So we need the z-scores for the x's, and the z-scores for the y's. Now on the homework, it refers you, you'll see a better printout of the page for the example for you to do in that download rather than view it online. So if you've downloaded the course materials, the page from the course materials has a better display of the values. They're already set up in a table like this to make it easier for you, whereas what you see when you go to the homework is a list of numbers that will be harder for you to work with. So in order to convert them to z-scores, we need the equation for the z-score. The z-score for x is equal to x sub I minus x bar divided by s sub x. And in the case of x, that's x sub I minus 5 divided by 2. Why 5 and 2? Because the mean was 5 and the standard deviation was 2. I gave those to you already. If you didn't know them, you know how to calculate them. You find the variance, take the square root, and you add them up, divide by n, you get the mean, and then find the variance. So you know how to do that. They were given to you in this case. So we need to subtract 5 and divide by 2. And the z-score for y sub I is equal to y sub I minus y bar divided by s sub y. And so that's equal to y sub I minus 100 divided by 15. Why 115? Because the mean of the y's was 100 and its standard deviation was 15. All right. So I'm going to take 3 minus 5 divided by 2. That's negative 2 divided by 2 is negative 1. Everybody clear on that? So I'm converting the score into a z-score. Right? Any questions? 5 minus 5 is 0, divided by 2 is 0. 3 minus 5 is negative 2, divided by 2 is negative 1. 5 minus 5 is 0. 1 minus 5 is negative 4, divided by 2, that's negative 2. 5 minus 5 is 0. 3 minus 5 is negative 2, divided by 2 is negative 1. 9 minus 5 is positive 4, divided by 2, that's positive 2. And 7 minus 5 is 2, divided by 2, that's 1. 1 and 1. So those are the z-scores for the x's. If you add them all up, they add up to 0. You find the mean of them, the mean is always 0. If you found the variance of them, the variance is always 1. If you found standard deviation is always 1. These are z-scores. Now we want the z-scores for the y's. We subtract 100 and divide by 15 to find the z-scores for the y's. So 100 minus 100, that's 0. 100 minus 100, that's 0. 70 minus 100 is negative 30. Divided by 15 is negative 2. 100 minus 100 is 0. 100 minus 100 is 0. 115 minus 100 is 15. Divided by 15, that's positive 1. 85 minus 100 is negative 15. Divided by 15 is negative 1. 100 minus 100 is 0. 85 minus 100 is negative 15. Divided by 15, negative 1. Another negative 1. Positive 1, 0. 130 minus 100 is 30, divided by 15, that's 2. Now again, the z-scores don't have to be integers, but I make up examples where the numbers are easy to do the arithmetic part anyway. All right, any question about that? So now we have the z-scores, but the formula says we need to multiply them together and then add them up. So, minus 1, so here's z sub x sub I times z sub y sub I. Minus 1 times 0, that's 0. 0 times 0 is 0. Minus 1 times minus 2 is positive 2. 0 times 0 is 0. 0. 0 times 1 is 0. Minus 2 times minus 1 is positive 2. 0 times 0 is 0. 0 times negative 1 is 0. Negative 1 times negative 1, positive 1. 2 times 1 is 2. 1 times 1 is 1. 1 times 0 is 0. 1 times 2 is 2. Any questions about that? Notice that all the numbers that aren't 0 are positive. That's a hint it's going to be a positive correlation because the average of these numbers is the correlation coefficient. How do you get positive numbers? Well, if the small numbers of x go with small numbers of y, you're going to have two negative numbers. 3 is small compared to these numbers. 70 is much bigger than the 3, but 70 is small compared to these numbers. So two negative numbers multiplied together are going to be positive. And if when x is big, 9, y is big, so 115 is above the average and 9 is above the average. We got two positive numbers, so two positive numbers multiplied together is positive. So if big goes with big and small goes with small, you're going to have a positive correlation. But if it's the other way around, small goes with big and big goes with small, you're going to have a negative correlation. So let's add them up. We've got 2, 4, 6, 8, 9, 10. So the sum of them is 10 divided by 14. And so that's about 0.71. That's a correlation of 0.71. That's what a 0.71, positive 0.71 correlation looks like. Now how good is a positive 0.71 correlation? Okay, any questions about how to calculate a correlation coefficient so far? So you need to memorize this equation right here. There are other versions, other formulas for correlation coefficients that are harder to work with, where you multiply the x's by the y's and multiply the means together and other weird things, but this is the easiest formula to remember. How to draw a scatter plot. I'm plotting each point goes on there, each case makes a point, right? And how to look at a scatter plot. We're going to try to calibrate our eyeball to looking at scatter plots. So how good is a 0.7 correlation? And here's the way to think about it. You square the correlation. So here's the correlation, and here's the correlation squared. And then you ask yourself this question. Imagine I woke up tomorrow, imagine you wake up tomorrow morning, and there's trucks, you hear trucks outside. You look out through the window, trucks are pulling up, and they say ABC, NBC, CBS, Fox, PBS. And you wonder, what are all these trucks? And you see the guys getting out of the trucks, they're setting up cameras aimed at your door. You're looking out the window, they're setting up cameras aimed at the door. And then all of a sudden a kid comes riding up on a bicycle saying, telegram, telegram. That's funny, because who in the hell sends telegrams, right? He knocks on your door, telegram, you open the door, and he says, congratulations, you've won the contest at the Brea Mall. Everything for you today, today only, 4% off. Would you get excited? No? So you know how to answer that question, right? So what you do is you square the correlation coefficient and you ask yourself if you'd be impressed if that was the percent off you got. All right? So if the correlation is 0 squared, you get 0% off. And if the correlation is 0.1 squared, that's 0.01, so you get 1% off. And if the correlation is 0.2, that's 0.04. That's the example I just gave you. Today only, everything is 4% off. All right? 0.3 squared is 0.09. That's 9% off. 0.4, that's 0.16. That's 16% off. 0.5, that's 25% off. 0.6, that's 36% off. 0.7, that's 49% off. So correlation of about 0.71, that's about 50% off. What that means is, if you knew nothing, you would have guessed 100. And how much would it cost you? $225. But if you use X to predict Y, using the right statistics formula, you get 50% off. So instead of costing $225 today for you only, because you know your statistics, it's $112.50. Would you go down to the mall today if what you wanted to buy for $225 was on sale for $112.50? Maybe you would, all right? It's better than nothing. Okay, so that's 0.707 would come out exactly 50%. 0.8 correlation, 64% off. 0.9 correlation, 81% off. How many would, if you got that certificate, the kid delivered it to you, would go to the mall today? At least at some point during the day, get down there and see what's... How about a correlation of 1? That's 100% off. Today for you, everything is free at the mall, all right? You needed that refrigerator, I don't know, they don't have cars there, do they? But diamonds they have, you could collect those and sell them, right? That might be your best deal. Go there and go to the jewelry store. Good luck. All right? So that's your way to think about a correlation. You square the correlation and think to yourself, would I be impressed to get that percent off? And I'm going to show you later that is precisely what's happening. That's exactly what's happening with the percent off. If you knew nothing but the mean, you would have guessed 100 all the time. But for this pack of cards, there is a correlation that allows you to reduce the cost of prediction by about 50%. Now notice the correlation is 0.7. You're not getting 70% off. You're getting about 50% off. You square the correlation to find out the percent reduction in the cost of playing the variance game. What's the variance game again? You're making predictions. Why do we psychologists care about predictions? Because you want to predict who's going to commit a crime, who's going to live longer. You know, the insurance company cares about that. You know, is your house going to burn down? The insurance company cares about that. You know, who's going to succeed in medical school? You decide who to let into medical school. Could you do better using this formula than you could by looking at whether they bought new socks? Yes, you can. So this is a better way to do it. All right, I'm going to post the results from the